Hello everyone, my name is Joe Furfaro, and today I'm really excited to share with you a bit about the project we worked on this week for the 2021 Microsoft Hackathon. Our project is called PhoTex, and it is a programming language we have created with an interpreter written in pure Python. It is a programming language made for designers. What does that mean? This allows technologically inclined designers who might be familiar with programming to use a code-based tool to create rich graphic designs that they might create in Photoshop or similar software or maybe Illustrator. This can actually make their job a lot faster and easier in ways that you'll see in this presentation, and is also a really good way to teach people how to code, but also enabling them to still do their graphic design work as well. So yeah, this is our repository, and all the code can be found here. I'm going to talk a bit about the premise of how it works and give you an overview of what the language is. So PhoTex is a plain text language. We've developed our own syntax for it. So the developer can write their code in a plain text file that specifies the different kinds of elements they want to place on their canvas. That might be shapes, external custom images, and text elements. So their code gets passed into our parser, which has two parts. The first part is our syntax checker. Our syntax checker basically makes sure that the way the user has written their code, where they put certain words and characters, is in the correct spots, and that it matches the grammar of our language. A grammar is basically a set of rules that describes what is allowed in the language and what isn't. Our grammar can be found here. This is written in Lark syntax. Lark syntax is a EBNF-like syntax that is used for the Lark parser. This is a great library that we've enjoyed using called Lark. It is a parsing toolkit for Python, as it says here, and what it does is it parses context-free grammars into abstract syntax trees that you can then look at and semantically analyze for your language. We loved using Lark. It helped us make our grammar really fast and validate it and get us a great syntax tree. It's written in pure Python, so we use that in our interpreter. So once the syntax has been parsed, we go into our semantic layer of our parser, which looks through the meaning of the program and the logic of the program. What that means is it does type checking. Did the user pass in the right type of variable here? We were expecting a color, but they passed in an integer. Okay, we need to tell them what line and column that occurred so they can fix the problem. We also check things like variable names. So you're trying to use a variable called blue. Does that variable actually exist? If it doesn't, we need to throw an error and say you're trying to use an unrecognized identifier here. So anyways, once we check the semantics and the syntax via our parser that we created, we go into our generation phase, which takes the objects that the user defined in their plain text and that was parsed and puts it into a tree, a hierarchy of objects that should be placed in the final output. The output can either be JPEG, PNG, or SVG, but all of our output is first compiled to SVG and then converted to one of the other two file types. So we take our object tree, and using our own built in-house SVG builder, we turn that into an SVG canvas object that we place all of the user-defined objects from the plain text code into. And we output it using this library svglib to help us write SVG objects to files. And yeah, that outputs to either SVG, PNG, or output image. So that's the overview of how our software works. And there's a lot of really cool features that we've added in. After this, if you want to stick around and learn more and see a demo of how this software actually works, we're really excited about it. We've included a kind of a longer coding tutorial and explanation of how these images can actually be generated from the code. But this is the overview of what we've done. But yeah, stick around if you want to see that coding tutorial where we've included a lot of the features that we haven't even had a chance to talk about here. So thank you very much. We had a great time this week. We learned so much. It was lots of fun. Yeah, enjoy the rest of the tutorial if you stick around. Hi, in this quick coding tutorial, I'm going to show you guys how to use the PhoTex language to create a simple image like we featured on the right here, which is just a little placeholder yin-yang image that has some weird stuff in here. It's got some different colors, some fonts, and some rotated text. So I'll show you that. So in PhoTex, you can create some definitions, and those definitions can be color definitions, font definitions, and custom types. Custom types are different objects, complex objects that you can use and instantiate instances of in your canvas, which generates this final image. So first thing I'm going to do is define a few colors. To do this, I write define color, and then I name that color, something I want. So I'm going to call it black, and I'm going to put in the hex code for black, which is just 6 zeros. I'm also going to define a color white and put in the hex code for white, which is just 6 Fs. I can now also define some fonts with define font. I can put a name of the font that I want to refer to it. I'll just call it Arial. I'm going to use Arial because it's on my system, and I will put that in quotes here as the font name. And then after that, I can put the size in points, so I'm going to put 12. And then I can also put an optional argument here, which is regular. I can put regular or thin or bold, and that's just going to specify the weight. But I'm just gonna put regular, so we get the regular font here. This is optional though; I could leave it out, but I'll put it there to be explicit. After that, we can define some custom types. I think this is all the colors and fonts we'll need to make this image on the right. So to do that, we can define a type. So I'm going to define left rect, which is going to refer to this rectangle on the left. In here, I could also set a preset size for left rect if I want it to be 100 pixels by 200 pixels always. But I'm going to leave that blank because I want to leave it so that when someone actually uses left rect, they can set the size themselves by passing in the width and height parameters. So I'm going to create this left rect. And an interesting thing about PhoTex is that the coordinate system is always based on the parent, and we feel that makes it really easy for the designer to place objects. So for example, in my left rect, the center is 0, 0, and anything I place is based on that coordinate system once I'm writing inside of this left rect block. So the first thing I need to do is place this white rectangle here, and the way I can do that is I can say rect, and I can place it 0, 0, which is right in the middle. The center of the rectangle is going to go in the center of this left rectangle space. And then I can give it a width and a height. So I'm going to give it 100 width, 100% width, and 100% height, which basically says cover the entire size of left rect. When someone creates this, they're going to pass in a width and a height. Whatever is passed in here, it's just going to be multiplied by this. A cool part here is that any of these numbers can be as complex math expressions as you want. So you can put in brackets here and write 6 plus 5h, and that will do 6 pixels plus 5 times the height of the parent. And you can do that anywhere. You can work with parent dimensions. Okay, so I'm going to leave that as that. And I can actually put in a fill for that left rectangle, so I'm just going to use white. I can also use explicit colors, so I could put in F and F, but I'm just going to use white because we've already predefined that color. Okay, so we have that rectangle. Now we're going to put some stuff in that rectangle, in that white rectangle. So I'm going to define a circle in the rectangle to begin. So I'm going to type circle, and the circle accepts an x, y, and a radius. I'm also going to put it at 0, 0, which is in the middle of this white rectangle. And I will choose the radius. And for the radius, I'm just going to do 20% of the width. Spoiler alert, I made this before, and this distance right here is 20% of the width of this big white box, so I'm going to put 20% of the width. And I'm going to fill that circle with black. I will actually put 0, 0, 0, 0 so you guys can see the explicit color definitions. Inside that circle, I'm going to place some text. And to do that, I will just type text. And then I will put the position of the text. So I'm going to do 0, 0, again, because it belongs in the middle of the circle. Remember that these coordinates are relative to the parent. I'm going to use the font Arial, which I defined before. I'm going to use the color white for this left rectangle. And I will put the text here right after in quotes what I want, and I'm just going to put yang in that left text. So some stuff you might be wondering. I don't know if you noticed, but these rectangles are actually outlined. The one on the right is outlined in black, and the one on the left is outlined in white, and also the text is rotated. So how are we going to do that? Before these types, you can actually use some modifiers we've created in the language to transform stuff in different ways. So this outside rect, it's white, but we want it to have a 2-pixel black outline. It's kind of hard to see here, but it's there. So what you can actually do is you can type outlined, and then after outlined, the program expects that you'll say the color and the thickness. So I'm going to say that this rect is outlined in black with a thickness of 2 pixels. And inside here, another modifier that we've created is rotated. So I'm going to say that this is rotated, and the rotation is clockwise. So I'm going to say that this is a rotated 90 text, and that will just spin our yang 90 degrees clockwise, which will produce this output here. So that's what we expect. And just as a quick little test, if I were to go over to my terminal, if I were to go over to my terminal and type Python PhoTex.py, and then our file was called demo.ptex, so I'm going to do demo.ptex. You'll see that we say registered 2 color definitions, 1 font definition, 1 custom type definitions, and it built 0 canvases. The compilation is finished. Great. All right, so from there, we are going to copy our left rect definition here and change some stuff up to build the right rect. So this time we're going to outline it in white. We are going to fill it with black, and we're going to put a circle in there that's filled with white instead. So I'll put FFF. And inside we're going to put rotated -90 because this text is facing the opposite way. And we're going to put yin, and it's going to be in black instead of in white. And that is our text. So we have created our left rectangle element and our right rectangle element. And I was explaining it, so we went a bit slow, but you can imagine how fast this would be to write if you were trying to create this yourself. Okay, next, I'm going to create a canvas. So what is a canvas? A canvas is the final object that I want to export using PhoTex. So to do that, all I do is type canvas and then the file name, the final file name that I want. So for me, I'm going to call it demo output.png, just like that. And after this, it expects 2 arguments. It expects a width and then a height in pixels. So I'm going to say this is a 500 by 500 image, and I'm going to open that up. And in here, just to check, we can go back to the terminal and try running our demo, and you can see there's actually an error. So our parser has caught here that it expected an escaped string after the word canvas. So the name of our file actually doesn't have to be in quotes. That's my mistake, but this is just an example of how the parser can catch errors like that. So if I try to compile again, you'll see it's built a canvas, but that canvas is empty, so there's nothing to put in there. So what we're going to do is we're going to place our left and right rectangles in there and see if we can generate that final image. So we're going to place 2 things. And to place stuff in a canvas, we would do it exactly like how we place stuff in a definition. So I'm going to write a left rect here, and it needs an XY and a width and height, because we didn't specify a preset width and height in these 2 definitions. So keep in mind that the coordinate system for this left rectangle placement is relative to its parent, which is the canvas. So you can imagine the whole 500 by 500 grid as the parent with 0, 0 in the middle. So we're going to place this rect at -25% of the width, so this much over. We're going to place it at 0, 0y. And for the height, we're going to give it 50% of the canvas. And for the width, we're going to give it, that's for the width. And for the height, we're going to give it 100% height of the canvas, just like that. And then after that, we're going to place a right rect. And we are going to give it a width of, an x of 25% width, because we're going to move 25% width over this way. A y of 0. Width of 50% of the width of the canvas, and a height of 100% height of the canvas. After that, I'm just going to go over to my terminal, and I will run PhoTex on that code. And it says, okay, registered 2 custom type definitions, that was left rect and right rect. It found the canvas, created generators, blah, blah, blah. And it successfully built 1 canvas. So let's head into VS Code here. And look here, and you can see a demo output.png has been created. And if I open that, wouldn't you see it? It says demo output.png, and it's exactly the kind of image we were trying to create, all compiled from this code. So to prove that I'm not making this up and I didn't spoof it all, I will show you that if I change this circle to randomly be red and I recompile this image, this circle is now red. So it is actually generating SVG. You can see here that if I open the parallel SVG file that was created with it, we actually have a completed SVG example of that image we created. So this could be moved online and used as a scalable vector graphic in more of a web environment. So we think this is a really cool software. And there's features we have in here that we didn't even get to show you in this video. It's just a short kind of explanation. But it was really fun to create. And we feel like it could be really useful for a lot of graphic designers. And we learned a lot this week and had a lot of fun. And that's all for the demo. My friend Mark is going to show you in the final tip of the video how the SVG, after the code is actually parsed, how does the SVG generator take that parsed object tree and transform it into this finalized image. So thanks a lot. Hope you have a great day.
Hi, I'm Mark, and I was part of the Shape Object class development team, as well as the exporter team. It was our job to take the abstract information provided by the parser and turn that into usable Python data structures that we could then loop into a tree and convert to SVG code. So, if the parser were to generate a structure similar to this, a canvas that had a rectangle element and a rectangle element as its children, and each of those rectangle elements had a circle in which had a text child, we would have to convert that into the corresponding SVG and then the corresponding PNG. This is the SVG that we will be generating, and this is the image it produces. Starting at the canvas level, we've designed a canvas class. The canvas class takes in a file name, the format in which you want to export to, the size of the overall width and height of the image, the list of children that it has, and a rotation if you plan on rotating the entire image. So, in our case, we have a test file in which we'll save as test.svg. It's going to be 500 by 500. It currently has no children and currently has no rotation. Once we generate the child objects, we can then add it to the canvas using c.addChild. Next, we move on to the rectangles, and we're going to give it the relevant information that they need. In this case, a rectangle takes in the following properties. Clipped, in which represents whether or not the rectangle would also mask its children, so a circle cannot grow bigger than the rectangle is contained in. A position of the center of the rectangle, the width of the rectangle, the height of the rectangle, if that rectangle has any stroke, fill, any children, or it is rotated. You will see similarities between many of the classes, such as circle, text, and the other shape primitives like ellipses, image, line, etc., because they all inherit from the shape interface, meaning that circle is resembling it for a good reason. It's because they inherit the same interface. Circle, however, instead of having a height and width, it has a radius, because that's what a circle would need. Similarly, text takes in only stuff relevant to text, so the text, the position of the text, the width of the text, the horizontal alignment and vertical alignment of the text, the font in which you want to use, the outline or stroke of the text, the fill of the text, which is its base color, the children of the text element, because even text can have children, and the rotation. Once we've defined all of the actual instances, we can start wiring them together to match this tree. So our canvas element, in this case called C, will need to add rectangle 1 and rectangle 2 as its direct children. Then rectangle 1 will add circle 1, while rectangle 2 will add circle 2, and then circle 1 will add text 1, and circle 2 will add text 2. Now that we've formed this tree, we can call the render function on the top level instance, and that will recursively be called on all of the children to form one SVG file. We print c.render purely for ease of use. We then call the export function, in which we'll both export to an SVG file just to be safe, and the expected PNG or JPEG file that you want to export to using the SVG lib Python library. To go ahead and see how this ends up looking once you've actually run the code, I'm going to go ahead and run that test case that we have provided here. Running the test case then prints the SVG so you can see what it looks like, prints the name of the file that you should look for that SVG, in this case test.svg, and also tells you that it is successfully exported to the PNG file, which is what we requested here. If I open the PNG file, there's our expected image, and if I open the SVG, here is the SVG file. This SVG file can be embedded into websites as well as brought into Photoshop or Illustrator for vector manipulation, which is extremely powerful to have. Even though it's not explicitly asked for by the user, it is still good practice to export these SVGs anyways, because they are just very powerful development tools. If you look, each one of these has a direct correlation to something that was in our code. SVG would map to the canvas element, our top-level container element. The defs is an instance inside of our canvas element. If we scroll to the top and look at the variables, you see we have a defs map, which is a dictionary of string to string. And inside each definition of the SVG file, is a relevant definition for the entire file. So this clip path is the clip path for shape ID 13802987946008, also known as rectangle1. Rectangle1 was given the property of clipped equals true. This is what this first input stands for. Clipped is true, meaning that it has given itself a vector mask. Any child that uses this clip path cannot escape this vector mask, which is why it's so powerful. Of course, we also have the G tag, which is a group tag, and this is meant to represent the children of a parent shape. So this rectangle has a corresponding G tag in which represents the children of this rectangle, specifically circle 1 and text 1. Similarly, this rectangle has a G tag in which represents its children, circle 2 and text 2. All of the information has been cleanly compiled within each of the classes. So if we go to rect and we look, we can see rect has a .render function in which we'll calculate the center. It will offset because rectangles are actually rendered from the top left, not the center. It will input that into a formatted string. It will compile all of the information and it will return that string. Once we have that entire string, we can write it to a file or print it to the console exactly like we have here. And once it's been written to a file, we can open that file and export it to the appropriate file type, such as PNG. And that's the general overview for how our data structures and exporter works.